I'm going to get started. So my name is Alistair, and this is Anup, and we're from Western Digital as part of the research team, and we're here today to talk about RISC-V with QEMU and KVM. So today I'm going to start with talking about the RISC-V Hypervisor Extensions, then I'll go into details about the QEMU implementation, and then Anup will take over and talk about the RISC-V port of KVM and the status and future work there, and if we have time, we'll have a KVM in QEMU demo, and then questions. So, the extension. So the extension was designed to support both bare metal and hosted hypervisors. The 0.4 version was released about 4 months ago, and today it's mostly what we're talking about. The 0.5 version came out today, so we haven't updated everything yet for that. So if you go look at the spec, don't get confused that not everything matches. We're talking about the 0.4 version. And all the feedback so far has been included into the spec, so we have feedback from virtualization projects, and that's kind of created the spec today. So Western Digital initially ported QEMU, XVisor, and KVM. XVisor and KVM are both hypervisors, and QEMU is an emulator. On the 0.3 version, we've updated it to the 0.4 version, and we'll update it to the 0.5 version. So this is what the hypervisor changes for the RISC-V spec. So RISC-V, without the hypervisor extension, has machine mode, S mode for supervisor mode, and U for user space mode. So this is kind of similar to EL3, EL1, and EL0 in the ARM world. And that's where you run your machine mode, your firmware, which is OpenSBI in the RISC-V, your OS, and your user space. So with the RISC-V hypervisor extension, it kind of splits the user space and your OS in half, and it looks like this. So your machine mode stays the same. It's not virtualized. It runs as it always does. And then your hypervisor runs in HS mode. So the cool thing about the RISC-V hypervisor extension is you can use an unmodified OS in HS mode and just run as you always did. You don't have to understand the hypervisor extension to keep running. If you want to use it, then you have to understand it. But you don't have to use it to just boot. And so your hypervisor runs in HS, then your non-virtualized user space runs in U, and your virtualized stuff, so your guests, run in VS and VU mode. So the hypervisor extension also adds a lot of CSRs. So CSRs are the control registers in RISC-V, and they're normally prefixed with the privilege mode that accesses them. So M status is the status for the machine mode, S status is the status for supervisor mode, things like that. So when virtualization is off in HS mode, we have all our normal SCSRs, and they do the same thing as always for supervisors. We now have these HCSRs, and so HCSRs are specific for the hypervisor. They're things that hypervisors are interested in. So controlling delegation and exceptions into the guests, things like that, and the second stage page tables. Then we have these VSCSRs, which is the virtualized guest SCSRs. So the hypervisor can read and write these and modify them and use it to load and save, restore context and things like that. And when you trap or change into the hypervisor, the hardware will automatically alias the SCSRs to the VSCSRs. And so this is what QEMU has to do. And so this means when your guest runs, it unmodified accesses SCSRs as it always would. But this really translates to just accessing the VSCSRs. So your guest can't touch the hypervisor SCSRs or the HCSRs. And when you swap back, the hardware swaps them back, so the hypervisor can save or restore the VSCSRs as it needs to. And there's a list there of what they look like. So the hypervisor spec also adds two-stage MMU. So the two stages kind of follow the same as the normal RISC-V stages. I won't go into details about that. But the first stage is, when you're virtualized, the two stages always run. So the first stage is for the guest. So Linux programs that as it always would, and it does your guest virtual address to your guest physical address. And then the second stage is controlled by the hypervisor, and it has to set that up as it needs to. And that can translate your guest physical address into your host physical address. I'll talk about more details about this when I talk about implementing it in QEMU. But it's kind of, if anyone knows the RISC-V MMU, it kind of follows the same way. It just loops through twice, basically. So we also have interrupts and things like that, obviously. So virtual interrupts are injected to the guest through the VCP register. So this is the interrupt pending register that's the virtual copy for the guest. So the hypervisor can set a bit in that for a pending interrupt, transition to the guest, and then the guest gets an interrupt. So we don't need a virtualized interrupt controller for the hypervisor to inject interrupts. So the hypervisor is also in charge of emulating SBI calls. So SBI is kind of like the PSCI equivalent in RISC-V, and the hypervisor will use that for timers and things like that. And with the two-stage MMU, the hypervisor can turn off access on the second stage, so accesses will fault into the hypervisor and use that to do MMIO emulation. So you can pretend to give devices to the hypervisor and trap and emulate that. RISC-V doesn't have an IO MMU or a virtualized interrupt controller yet, so that's kind of the only options you have. So just a quick comparison to ARM, which is kind of similar. So the RISC-V Hypervisor Extension doesn't have a separate privilege mode or anything like that for hypervisors. This is different to ARM, which has EL2. This kind of helps with running both type 1 and type 2 hypervisors, because you don't have to trap back down to below if you're an operating system. And like I just talked about the VCP, the hypervisor injects interrupts to the guest using the VCP register, so you can set bits in there and then transition in, so you don't need a virtualized interrupt controller. The RISC-V extension uses SBI calls, like I said, for timers and IPI. That's different to the ARM implementation. And the RISC-V Hypervisor Extension supports nested virtualization. So ARM supports that recently, but it's there already in the RISC-V Hypervisor spec. So the VTVM and VTSR bits basically tell the hardware to trap into the hypervisor when the guest does certain things, like SRETs, S-fences, and page table accesses. And so this allows you to then trap and emulate to do nested hypervisors. So the extensions in QEMU. So there are patches on list now adding support for the hypervisor extensions, the 0.4 version to QEMU. This works for both 32-bit and 64-bit. Everything we talked about just then is supported, so VS CSRs and swapping those, QEMU will handle that for you. QEMU will correctly delegate interrupts to the hypervisor, which then has to delegate them to the guest with the VCP, and there's a two-stage MMU. So if anyone's interested, there's a link on the slides of how you can take it. You can also just get the patches on the list if that's easier for you. So there's a QEMU kind of standard thing we're going to go with where draft specs are going to be disabled by default. Because it's a draft spec, it's subject to change in not backwards compatible ways. So you have to enable it with the -CPU argument, which is shown on the slide. And we have x-h, which is a QEMU way of saying it's an experimental feature. So it's an experimental feature with a hypervisor extension, and you can enable it with true. So we have some changes made to QEMU already. The first one's actually not, I thought it was going to be merged, but it's not merged yet still. But let's just pretend it's merged. So we want to remove the requirement on the MIP CSR to be atomic. So it's interrupt pending CSR for a CPU. So we previously updated it atomically because other CPUs would inject IPIs into, so they would change the status of it. And having it updated atomically is a real pain when you are swapping the status all the time as you trap in and out of hypervisors. So we now use IOthread, or hopefully we'll use IOthread, to be able to do that, which is, for QEMU people, that's kind of the standard thing QEMU does. So we allow sending the ISAs via the command line, like I just talked about, so that way we can disable it by default and allow people enabling it, so we don't break everyone who expects to use some older version and then we update it and things like that. And we have to consolidate some of the floating point disable logic. So we have to maintain the hypervisor state. So QEMU always has to know if we're virtualized or not virtualized. This is pretty straightforward because we only ever changes on traps or returns. So there's only a handful of places where it can change. But the weird thing is that M mode and HS mode, which are not virtualized, can both pretend to do virtualized accesses. And I'll talk about this on the next slide with the two-stage MMU where it comes up. So QEMU needs to know this and handle this. So it's not just as straightforward as are we virtualized or not. And we also need to be able to delegate faults to guests. So there's some faults that no matter what the delegation settings are, we have to fault to the fault to the hypervisor. And so the way QEMU works is a second stage fault in the two-stage MMU lookup has to fault to the guest. So that happens in the TLB fill, which is very different to where we handle exceptions in QEMU code. So we somehow have to maintain the state between those two. Right now we do this with the force HS-exep, but that's changed in the 0.5 version. So we'll probably be getting rid of that and replacing that with a different way in the 0.5. But that just happened today. So that's, yeah, we haven't done it yet. So I don't know how easy that is to see, but the two-stage MMU, so like I said, when you're virtualized, the two-stage MMU is always on. You can do one-to-one mapping if you're not interested in using it. But so the M-status MPRV and H-status SPRV are what M mode and HS mode use to turn on two-stage MMU accesses for loads and stores. So the reason you'd want this is if you trap into the firmware or your hypervisor for, let's say, an illegal instruction, it's then your hypervisor or your firmware needs to know what that instruction was, so you can do a load or access on the address that you have and get the information from that back. So that's why you would set these bits. So the code changes to look kind of like this. So the guest physical address, we have to now pass in if we're in the first stage or not, and if we're doing a two-stage lookup. So we need to know if we're doing a two-stage lookup because the page table walker has to go through the two stages for every access when you're doing a virtualized, when you're looking up from a virtualized state, and even in the first stage. And we need to know if it's first or second stage because we access different CSRs depending on the stages. And the TLB fill function, yeah, maybe you can see that, but the TLB fill function changes to look like this. So if we're virtualized, or if we're pretending to be a M or HS status access, two-stage MMU access, then we go through the two stages. So we do one, and then if that passed, we do it again. And so we change the values and reuse them. But it gets a little more complicated than that again, because if you're virtualized, and on your first stage, use the SATP register, which is the guest's page table register, to do the lookup. But if you're not virtualized, but pretending to do a two-stage lookup, then you have to use the VSATP register. So there's just all these things you have to keep a track of, depending on how you're accessing it and what you're trying to do. And so there's not really any way to avoid this. You just have to kind of keep an eye on it. And like I said, the second stage translations have to trap back to the hypervisor. So that's something else you have to keep an eye on. So the other hard thing to do in QEMU is the register swapping. So some of the CSRs are aliased kind of between the different privilege modes. So M status is the overall status of your core. And S status is just M status with masked out. So the supervisor doesn't get access to everything, it gets only these certain bits that are passed along to it. So QEMU uses M status and some of these other CSRs to maintain the state. There's nowhere that says what privilege mode you're in, it's kind of saved in, well, some of the stuff, it's only saved in the M status. So you have to read the value back from M status. So this gets really difficult when you're swapping these bits around all the time as you enter and exit virtualization modes. So for M status and MIE, we use pointers, and I'll explain that a little more in a sec. For the other ones, we can just value swap, which is easier. And the MIP CSR, now, let's pretend now it's no longer atomically accessed, it's value swapped as well. And so it ends up looking like this for the pointers. So on hardware, if you access the S status CSR, if you're virtualized or not virtualized, you'll go either through S status or VS status, which is backed by a real M status. In QEMU, if you access M status, it either points to M status no vert and M status vert, and we handle swap when they swap, copying the right values around. And if you access S status, it's the same thing, but just masked out. So this is different to the other implementations in QEMU, which have arrays and then access indices in the arrays. So if you're not virtualized or virtualized, you access the 0th or the 1st or whatever indice. The reason we do it like this in QEMU is that the hypervisor extension is, because QEMU is so modular, because RISC-V is so modular, there's a lot of people who don't probably want to use the hypervisor extension. And if they're adding some other extension, they don't care about the hypervisor extension, we don't want them to have to worry about it. So in this way, M status, S status, all these registers are always correct. You just access it and you don't have to worry about which element in the array do you access, what virtualization mode are you in now, things like that. And so the idea is to help make it easier for other people who aren't interested in it to use it. And we kind of keep all the hypervisor stuff self-contained and handle swapping there. So it makes it probably a little messier in some places, but the idea is that other people don't have to deal with it if they don't want to. So the future work, so we want to upstream what we currently have. It's being reviewed. If anyone's interested in reviewing, the more reviewers, the better. We have to implement the 0.5 version now, as of today, so get started on that. The other thing is updating TLB's caching index to include virtualization state. So right now, you can, so QEMU caches TLBs, and you can flush either all of them or certain ones. So right now, we flush everything at pretty much whenever there's any chance something could be cached, or something could be a problem, we just flush. Which is probably a performance overhead, but more importantly, it's going to cover up bugs. So if your hypervisor doesn't correctly flush TLBs, then it works in QEMU, but it won't work, but then you run on hardware and it doesn't work. So we'd like to change it to flush at least the right virtualization mode based on S-vents or H-vents, depending on what we can do there. So we should be able to do that. I'll update the last specs as is there again. And the nested virtualization. So I talked about it at the start. It's in the spec, but it's not in QEMU. We just haven't connected it, and we have to test it. And then 32-bit Linux guests don't work. So we have to figure out why. If anyone also has an idea on that, that's a good one in the review. So now I'm going to hand it over to Anup, who's going to talk about KVM.
Thanks, Alistair. So I'm Anup. I'll be talking about the RISC-V port of the KVM hypervisor. Yeah, so it's like the first type 2 hypervisor for the RISC-V world, and and the RISC-V H extension, as he mentioned, is very well suited for the KVM hyper, and partly also because we have been giving a lot of feedback from the start itself from 2 different hypervisor perspectives. So for KVM RISC-V, the host Linux will be running unmodified in HS mode. Only the KVM RISC-V kernel module would be using the H extension CSRs. And the guest Linux also will run unmodified in the VS mode. And yeah, these are the same layers of the software which he showed. And the color coding is different based on the privilege mode they run in. And so some of the key aspects of the initial KVM RISC-V port are as follows. So we have ensured that we really don't introduce any RISC-V specific KVM IOCTL in the ABI. So far, we have tried to ensure that. And the world switch is so far minimal, and we hope that there won't be much changes in the world switch in future as well. And most of the save restore is done in the load input interface, through the load input interface. And the floating point is also saved in a lazy way because the architecture supports it. So we don't need to save the floating point for a guest or guest VCPU if it's not using it. And we have a KVM OneReg interface for the user space, so that user space tools, the QEMU and KVMTOOL can access the VCPU context. And for timer and IPI emulation, it's all done in kernel space. And the PLIC emulation or the interrupt controller emulation is as of now in the user space. We might do it in kernel based on the performance gains in future. And we have huge page support as well for the VMs. It works fine so far. And we also provide SBI interface to the guest, emulated in kernel, of course. And the unhandled SBI calls will be definitely forwarded to KVM user space. So there are certain calls which we really cannot emulate in KVM kernel space. So we'll be forwarding such calls to user space. Yeah, so these are the SBI calls which are already there in kernel. So this table shows the 0.1 SBI calls. And we also have a 0.2 SBI spec in draft stage, which is much more modular and extensible for future. But it's not spec'd out actually 100%. So SBI is nothing, as like he mentioned, it's a PSCI equivalent of the RISC-V world. It's a syscall style interface between the host and the guest. And the same interface is also provided by the platform specific M-mode firmware to the host kernel. So this is how the traditional KVM run loop looks like. It's a nested run loop which looks same on across architectures. So I've tried to show this in more in context of RISC-V, with the same color coding, like what part of the run loop runs in which privilege mode. It's obvious like the user space will be continuously doing the ioctl run, and in the kernel space we'll be doing the load and put once when we enter the ioctl, and then the most important function is the vault switch that we have, which does the host to guest and guest to host transitions. And the usual exit conditions for the KVM RISC-V are host interrupts. When we get a host interrupt, we'll come out of the guest mode, or it will come out of the guest mode when there is an MMIO trap or an SBI call or an stage 2 trap. So most of the exits we'll try to handle in kernel as usual, in the in-kernel loop itself, but sometimes like for the MMIO exits and for the unhandled SBI calls, the SBI calls which you cannot handle in the kernel space will be forwarding back to the user space. So right now there are only 2 such calls, which is the console, from bottom last. So console put car and get car, so which is like VM specific. So these are used for early prints and debugging. So this cannot be emulated in kernel. So we forward this right now to user space. So in future there will be vendor extensions in SBI 0.2 defined. So for those kind of SBI calls, we'll be forwarding to user space. And this is another high-level view of the in-kernel KVM group mentioned in the previous slide. So it does a lot more things than shown over here, of course, but we have tried to highlight the important parts of it. So first thing it does is try to check if the ioctl run is called after an MMIO emulation handled in the user space, or it was an SBI called handled in the user space. And then in the loop itself, we flush the interrupts just before entering the VM or the guest, and when we hit an exit condition, we first sync up the interrupts, because there are certain bits in the VSIP registers, what he mentioned, like which can be updated directly by the guest VCPU. So we sync up the interrupts and then process the exit. So VCPU interrupts are modeled in a quite unique way, at least for the RISC-V port of KVM. And we have modeled it around multiple producer, single consumer. It's totally lockless. We don't have any locks. So basically, we have 2 atomic bit maps, which we update using bitops atomic of the RISC-V. So one is IRQs pending, which represent the current state of the interrupts of that VCPU. And there is IRQ pending mask, which is if there is any changing in the previous marks IRQ pendings, then that bit will be set. So we have various sources of injecting the interrupts. One is the user space itself, where the PLIC emulation or the interrupt control emulation in the user space wants to trigger an interrupt. Then we have a timer events getting expired in the KVM kernel module for the VCPU. And then we also have IPIs injected from other VCPU of the same VM injected using SBI calls. So we have multiple producers, and in future it might even increase. So that's why it's modeled around multiple producer and single consumer. The consumer is just the run loop. The run loop will be consuming all the changes in the IRQs pending and pending mask and flushing it to hardware. So the vault switch, like I mentioned, does the host to guest and guest to host switching. It's totally written in assembly. It has to be done with interrupt disabled to ensure atomicity. And so right now, to give some numbers, the kind of overhead what we have is we save 24 CSRs, GPRs, sorry, and 4 CSRs, and restore 3 CSRs and 31 GPRs roughly when we do host to guest, and the reverse when we do guest to host. And the most important part is when we are in guest mode, the HS mode or the hypervisor STVEC points to the return path, and the scratch of the HS mode points to the VCPU context. So this helps us get the register state back and ensure that we return to the same place when the exit happens. Yeah, and this is like a current state of the VCPU context. We only have GPRs, CSRs, and some FP registers, but this will definitely grow once we have more RISC-V extensions, like vector extension is already in pipeline. So this context will keep growing, but we don't hope that there will be much changes to the vault switch. And like I mentioned, we are providing one reg interface to the user space for accessing the VCPU context. And we have 5 types of one reg registers with config register, co-registers, CSRs, FPF, and FPD. So FPF is 32-bit floating point, and FPD is 64-bit floating point. So most important one is the ISA config register, which tells the capabilities of the VCPU that we are providing to the VM, and this can only be written before running the VCPU. We cannot update it after the VCPU is already running. So current status and future work. So patches are already sent out. The first version was sent out in July 29th, and then it was reviewed quite fast. Like by V6, we already had most of the patches reviewed or act. And recently we sent out V9 of the KVM RISC-V, and then KVM tool and QEMU patches are still blocked because we want the KVM RISC-V to be merged in kernel first. So this is the first link is the official location of the our KVM RISC-V Git repo. And then we also created a wiki which will help users. Right now we just have one useful page to help users start and play around with the KVM RISC-V on QEMU for 64-bit. Yeah, there are a lot of things to still do actually. We have to move to the new draft version 0.5, get 32-bit working, bring up on real hardware. Then SBI 0.2 is there in pipeline. And we need trace point supports, KVM unit test support. Vector extraction should be virtualized when they land in the spec. So, yeah. And upstream the KVMTOOL and QEMU changes as well. In-kernel plic emulation is also being considered based on the performance gains. Then eventually migration support, libvirt support, and so forth. Yeah. So I have a demo. I guess we have time. So I'll quickly show running a VM on QEMU with huge pages and without huge pages. So I mean, I don't have time to just compile everything, and it will take time. So we just booted a host with the KVM patches applied. It's 5.4 RC3. So and the KVM kernel module is like built-in, not pluggable, but we can just even plug it at runtime. And we'll create a VM with 2 vCPUs. Yeah. And meanwhile, we can take questions.
So as I understand it, this is one case where we have some sort of hardware-software co-design.
Yeah.
And I was wondering if you had given some consideration to having your two-level page, having basically an HVA to GPA cache or page table or something, instead of having two levels of lookup, and whether you had tried to evaluate whether this would save time or. Well, a discussion about that to know whether they had considered a cache or considered a page table to do that or discuss that.
I guess for that, it's kind of a bigger change for the spec perspective. But yeah, I mean, it's not considered, I think, and maybe it can be brought up actually. But I think at this stage, I don't know how big changes the spec folks are ready to take. So it's almost freeze. They are not doing any breaking changes anymore to the spec.
But this has not been discussed as the spec was brought up?
I guess Paolo was involved initially, right?
So the question is whether, so from what I saw, I think on slide 8 or something like that, the two levels are HVA to, no, sorry, guest VA to guest PA, and then guest PA to host PA. And I was wondering about a cache or a page table maintained by software that would do directly guest VA to host PA.
Guest VA to?
Host PA.
Guest VA to host PA.
So that the hardware would do only one lookup.
Guest VA to. So that is possible with unprivileged accesses actually. So there is something called as unprivileged accesses in RISC-V, where the host or the hypervisor can do load stores on behalf of the guest. It's not exactly AT operations of ARM, but it can actually fake the load store operations as if been done in the guest or VM. So that can be used to do full two-stage translation from the so that you can access the guest VS like a guest would access directly, and you can.
No, I was really talking about is the hardware having a table like this, so that basically the hardware would do one lookup.
Okay.
I think the TLB, the way the instruction set is designed, you can have combined translations in the TLB. I don't know if there's any hardware that does that. Actually, I don't know if there's any hardware that does the hypervisor extension at all. But it's certainly not forbidden by the spec to have combined translations in the TLB, so that you do two lookups when you have a TLB miss, but then the TLB does the combined translation. And I think that you can disable the stage 2 translation. Like, it's always there, but the HGATP can be like no page table.
Yep. Yeah.
Yeah, and then you only have one, and you can do shadow paging in KVM, but it's not done yet, and I don't think that you plan to do it, I guess.
Okay. Yeah, so the guest is booted like we have 2 vCPUs. And
very quick question, are you going to implement this in Swerve?
So Swerve is like M mode only CPU right now, 30-bit. Maybe in future they might go that route, yeah. Questions? Sorry? Yeah, I'll quickly run with huge pages as well.
Hi. So I think that, and maybe some of you will disagree with me, but I think that one of the mistakes that we did in a KVM Intel module is that currently the only way to specify to it which VMX features with hardware virtualization extension to use is only based on hardware capabilities and kernel module parameters. And I personally dislike this because I think a lot of times you want to control it on a per VM basis instead from user space. So just as a tip, I think that your KVM RISC-V module, I think you should not control in KVM module parameters with hardware hyper extensions you use, but instead control it from user space to not repeat the same mistake.
So, I guess most of the settings are per VM basis through the KVMTOOL and QEMU command line itself.
So today, I'm not talking about the CPU ID like features exposed to the guest. I'm talking about what are the actual hardware features that you use of the H extensions.
Okay. So as such, as extension is pretty much single feature. It's not a set of features as of now.
So how do you discover?
It's not like Intel where there is it was built over time with gradually with more feature bits. So right now it's just H extension means you have this set of hypervisor capabilities. Maybe in future when some new hypervisor feature is added later on, then in that case, yeah, makes sense to have a parameters to stop the kernel module only use certain features.
And I have another question. Does RISC-V stage 2 MMU, because I'm not aware of it, does it support execute bit that depends on the guest privilege mode, whether it's running on U mode or S mode? Or is it a standard execute bit on the that is global?
So all guest pages are treated like user level pages in stage 2.
No, I don't mean like the references to the stage 2 MMU. I'm talking about whether I can define a physical page in the guest physical address space that is executable or not based on whether the guest is running in U mode or S mode.
So right now it's like execute or not execute. You can specify the execute permissions in stage 2 page table.
Yeah. So the reason
it applies to both S and U.
Yeah, so the reason I'm raising that is because if you look in the future on, for example, what Hyper-V is doing with hypervisor code integrity, that you want to specify that the guest kernel only have executable pages that are signed, but in user mode you want to allow everything. This is why Intel created a feature called MBEC, which is mode-based execution control, that you can control executability based on the ring of the guest. So you probably want to add something like that in RISC-V so that you will be able to also implement in Linux, for example, in the future, hypervisor code integrity feature.
Sure, that's a good suggestion. Yeah, can be discussed. Yeah. Yeah. So this is a guest booting with huge pages as well. Yeah. It's there. I think there's one question there. Yeah. Sure. Sure. If you have more questions or want to discuss, please catch us. We'll be around for 2 days more. Yeah. Thank you. Thank you.